Hello and welcome to the third tutorial of our series. During tutorial number 2 we have modeled out this guy right here. We basically just used hard surface modeling techniques and a little bit of Grasshopper for creating that pattern there. And during this tutorial we're going to look into element type 2, and I'm going to kind of model it out. I wouldn't say model, but I will create it in a completely different way. So with the use of Grasshopper and in this case structural optimization. So to get started, I'm going to just make a copy of it, just so that I don't need to deal with overlapping geometry. So I'll just create a box here. I'll just move the box away from the side. And actually I'll leave the box. Wait, no, we won't need it. So I'll extract the silhouette of the box. This will give me the wireframe. I'll lock it in place, delete the voxel, and okay, so we have the frame there. So as a guide, I'll just create a single surface representing the same element that we see here, from midpoint to midpoint. There's nothing fancy about it. And then I will just grab my guide curves here. So in this case I only care about the outer boundary and the curve here, and the points here, sorry. Actually the border as well. I'll just make a copy. So I can see that I don't really need for the bottom part for how it connects. I won't need to do anything about it. I can just simply take it, make a copy from it, put it there, and I have a guide that's going to help me understand where the joints are going to be placed in the correct position. And for the side here, the horizontal part, I will just simply rotate it 90 degrees and select that part, move it in place like that. Okay, so we have the bottom part and the side part done. Now I'm going to deal with the short sides here, which are this type of element. Again, I'll select the boundary, I'll select the 2 points for middles. I'll grab the rectangle just as a guide for actually placing it in the correct position, and I will just simply rotate. Rotate, move it into place, and actually copy it from here to here. So that's quite simple. Okay, so now I have everything set up here. I don't really need the surface anymore, so I'll just delete it. So that's my guide. Okay, so now instead of modeling it out, I will use what's called structural optimization. And it's a voxel-based procedure where basically a Grasshopper script carves out all of the unnecessary geometry and according to certain stress loads or stress flows throughout the voxel space, and it leaves only the geometry that's needed to basically for the object to hold that particular load in that particular point. So to explain this better, if I have, let's say, a box, and I'll just do a 10 by 10, oops. If I have a box and I'll just do 10 by 10 by 10 box here, and let's say, let me just make a copy of it, smaller, something like this, and I'll just do something like this. So let's say this is an area or some sort of a block on which the element, our imaginary element, would rest, right, on top of this block. And these two blocks right here are like, let's say both of them are 1 kilogram each, right? So they want to fall down. So you could kind of model out some sort of a, some sort of a shape, right, that holds them and doesn't let them fall down. But that particular shape is not really, it's too much material there. So you could start thinking that, oh well, maybe I need to cut away that part, and maybe I need to cut away that part, and this part is not doing anything, right? So you start cutting those away. Instead of doing that manually, you can use Grasshopper to optimize it and to generate a form that has the smallest amount of volume possible while still being able to hold these two elements, basically connect the base with these two elements, right? So to do that, actually let's stay to this to this example. So I'll just isolate it. Okay. So to do that, I will be using a plugin for Grasshopper that's called Topos. There is also a plugin called Millipede, and I'm not sure if Caramba does voxel-based topological optimization, but there is also like other structural plugins out there. But in case of Millipede, it doesn't let me do more than, I think, more than a single area of support. So I chose to use Topos, which is right here. You can download it for free from Food for Rhino website, right? Just hit download and you'll have it. And just follow the instructions on how to load it into Grasshopper. There's a bunch of tutorials on it and a bunch of guides on it. So just figure it out. And basically the way I work with anything that uses a solver, that uses some sort of a brain, right? I work backwards. Usually in Grasshopper you work from left to right. In this case, with something like this, I will be working backwards, because I know for a fact that everything will go into the solver of Topos, which is called Optimus, right? So everything is going to go into this guy right here. And to make the system work, all I need to do is, while working backwards, fill out or plug into every empty input that this solver requires. So let's start. As I have it in my Grasshopper screen, it has 3 inputs that are needed for it to work. So R, RS, and M. Okay, so R is run. It just basically asks us for a toggle. And I'll have it as false for now, so that it's not running. RS is reset, and it's asking us for a button. What else is there? M is model. Okay, so it's asking us for a model, and I know that it's a part of Topos plugin, so it's an internalized type of information for this particular plugin. So I'll go to model creation, and I'll find just model, and I'll plug it there as well. Okay, so now we still have 3 inputs here that are empty. Let's go through them real quick. Subdivision threshold, that's fine. Let's leave it as a default. I'm just giving a really quick, simple tutorial on this. You can go really deep with this, but for this purpose, it's something simple. Optimus parameters. default parameters will be used. Well, let's see how it deals with the default parameters. Or do we have parameters here? Let's see what we can change. So I'll plug in Optimus parameters here. And let's see, optimization iterations, advanced parameters, penalty, charge, and sensitivity filter. Okay, so let's use custom Optimus parameters, because here I want to change optimization iterations. Just to make it quick, for now I'll use like let's use 11 iterations. So I'll just use a slider for that, and later on to make it more accurate, we can increase this a little bit. Don't go overboard with this though, it will become really heavy. Analyzer parameters, let's see. Analyzer parameters we have here. I'll connect it like so, and let's see what we have here. Iterations, maximal number of iterations to estimate solution. Okay, let's use something like 2000 for this one. The way it works, well, I'm not sure, I just assume, but every time when it optimizes, so it does that step by step, right? So every time that it does one step of optimization, then it does 2000 steps of analysis, maybe, and then according to the data that was gathered, it does another step of optimization, and that then does another set of analysis iterations. So it's like nested steps. I might be completely wrong about this, so don't quote me on that. This is just how I assume it works. Okay, so we have a model here, and it says GPU mode. I'm doing all of this on a laptop, and my GPU is much weaker than my CPU. So instead of using GPU mode, I will right click on the model name, on the node name, and I'll choose CPU mode. So it's going to be much faster for me. Okay, let's see what we need for the model. Boundary domain, boundary conditions, I assume. Yes, boundary conditions, boundary properties, and model resolution. Okay, let's start with boundary domain. I'll go to model creation tab, and I'll find boundary domain. I'll just connect it like so. And let's see what boundary domain needs from us. So it needs domain mesh to create modeling. Okay, so everything that's going to be simulated is going to be simulated in some sort of a boundary, right? In some sort of a world. If it's infinite for simulation, then it would mean that it would take infinite amount of times, and infinite amount of voxels would be created for the simulation, right? So we need a certain boundary. I'll be using this box right here as a boundary, and this is basically how big, what's the maximum size of the element that's going to be created is going to be, right? So I'll be using this as my boundary. Okay, and it asks me of a mesh, but I assume as long as it's a single closed brep, set1 brep, as long as it's a single closed brep, it should automatically mesh it by itself. Yeah, it doesn't seem like it's making a difference, so I'll just reference in a brep and connect it there. Density value, default is 1. I'll leave it as default because I don't know what it does. And then we have y and p parameters, and we need to plug those in. So y is Young modulus and p is Poisson number. Okay, let's say our element is aluminum or aluminium, right? And then let's just say aluminum Young's modulus, like that, something like that. Or can we just get aluminum properties? Yeah, there we go. Aluminum properties, and here I'll just find Young's modulus, so what are these? Minimum maximum value in SI units. That's perfect. Okay, Young's modulus is between 68 and 88.5 for aluminum, so I'll just use something in between, 75. Let's go for 75. 75. And poison value. Oh, there we go. Poison's ratio is between 0.32 and 0.36, so 0.34, somewhere in between. 0.34. I'll connect that. Honestly, it doesn't really matter if you're using aluminum or you're using plastics or something like that. I just chose any material that I could think of. Okay, so that seems to be working. Next one is boundary condition, load and support conditions. Okay, so let's go to model creation again and find our boundary conditions node that we directly connect here. And it asks us for two things. One is for where are the loads, and second one is where are the supports which are holding the loads. And in this case, I will, let's do something fancier. Let's have two supports and two loads, right? So these are going to be my supporting blocks that are going to hold my element in place. So for supports, it just asks me for a mesh. That's perfect. I'll just create a mesh, not a mesh, brep, set multiple breps, connected there, didn't turn red, so probably having a brep there is fine. I'll hide it. And now these are my loads, so I'll create a brep component for them as well, set multiple breps, hide both of them, and wait. No, this one doesn't ask me for a mesh. This one asks me for something else. It asks me for a load, so I'll go to model creation. Oh, and here we can see that there are different types of loads: linear, point load, surface load, and volume load. Since here I'm dealing with two volumes, in which the load is going to happen, I'll be using volume load, like that, connected there. And now let's see, a load mesh and load vector. Okay, so load mesh is simple. Load vector, so I want the load to be downwards in z-axis, so I'll just use z vector, unit z. You just double click, type in z, use unit z, and it needs to be downwards, so it's gonna be negative. And I don't think it matters if I'm just using one vector or two. Yeah, that's fine. Let's see if it's going to work. Okay, so I have my two meshes in the top, which are pushing downwards. I have my two meshes or boxes in the bottom, which are holding everything up, and the structure is going to be calculated in between those. Why is this still orange? Input parameter R failed to collect data. Okay, so boundary properties, we don't care. R, model resolution, data. Okay, so it needs resolution, and it doesn't want a number. There we go. There's a resolution node right here. I'll just connect it like so. And it asks me for size of element. Okay, so it's not the amount of how many voxels we have in X, Y, and Z, but rather the size of the voxel. I know that this is 10 by 10 by 10 units big. So if I do the size as 1, yeah, each voxel is like 1 unit big. That's fine. Okay, and here it even draws the nice little icons showing where the load happens and where the supports are. That's nice. I'll be hiding everything here so that it's not in the way. Actually, I want to see the boundary. Or do I? No, I don't want to see the boundary. I want to see the supports and the load meshes or boxes. Okay, so Optimus here. The output from Optimus is something that's, yeah, that needs meshing for sure. So once we get the output of it, we still need to create a mesh from the output. So I'll go to model data and I'll choose ISO mesh, like that. And here it's going to ask me for ISO value. So my assumption is that ISO value should be 0.5. Something like this. Okay, so a mesh is created. That's nice to see. Actually, everything's transparent, so that's hard to understand what's going on. So I'll just create a preview, a quick custom preview for it, just to see better what's going on. So that seems to work, but it's not optimized at all, and there's some weird stuff going on there. And as I increase or decrease the value, it kinda... Okay. Let's go back to 0.5. Let's just see. Is there anything else I need to change? Yes, two things. First one is object parameters. Here we have what's the fraction of the volume that it needs to keep, right? So how much material should it carve out and how much should it keep? So right now it's set to 0.2, meaning that it's going to try and keep 20% of the material. I'll go for a more aggressive approach and I'll just say keep 10%, and we'll just see if it manages to do so. And one last thing before we run the simulation, I will right click on the solver itself, and instead of using final preview, I'll choose live preview. Because what this is going to do is it's going to show me every step, so it's going to be easier to understand what the heck is going on. Right. So now I'll hit reset, I'll hit true, and I can see it tried to do... Well, I guess it's not wrong. I mean, but it's definitely not a very stable structure. So it did do the optimization quite well. And by the way, I can thicken or make this thinner by just increasing or decreasing the amount of the ISO value itself. So it did do it. It's a very boring thing. So for optimization iterations, I'll just choose something like 30, something more. Let's run it again. Yeah, it's always going to do something like this, isn't it? I seem so. Sure, why not? I guess that's fine. So now I can start messing around with it, right? Right now it's just doing 2 columns, but for in our case, for our element, we'll need it to be one single element. We'll see how that turns out, but at least now we know that it does work. What if we choose volume fraction to be like 30% rather than 10%? Let's see. Ooh, that's neat. A little bit broken, but much better. Let's just see how it looks like. Okay, that seems nice. There are certain things that I don't like about this. The first one is these boxes, these support boxes, kind of carve out the element. If you understand what I mean. There are these kind of incisions in the element where the support boxes are. So I want to get rid of those. I want that to be filled in. So if I remember correctly, that's under boundary properties in the model node. So I'll go to model creation, I'll choose boundary properties. Okay, it's immediately red for some reason, we don't care. I'll just connect it as my to my boundary properties input, and where it says fixed mesh, I'll just simply connect my supports and my load B-reps into it. No mesh for provided density, or provide at least one density parameter for mesh. Okay. Density, we saw it here, and it's 1 by default, so I'll just assume if I plug in 1 here, it's going to start working. And if I run it now, no, it doesn't work. Okay, what if we say 0 and run it? Also doesn't work. Huh, that's strange. What if we do 10? At this point I'm just guessing, as you can see. Also doesn't work. Okay, do we care? Huh, it works for this one, but doesn't work for the supports. What if we flatten this input then and run it now? Nope, still nothing. Okay, that's fine. We will fix it manually. That's okay. I don't want to waste time trying to figure out what's wrong with it. So as long as everything works, we're happy, and it seems like most of the things are working, right? So boundary properties, I'll keep it. I'll keep it. So right now the resolution size is set to 1, and it's a bit, big. So instead of using 1, I'll choose 0.5 or 0. Yeah, let's go for 0.5. Keep in mind it's an exponential growth of how many polygons there are, so even with 0.5 it's going to become much heavier, and it's going to take much longer to calculate. So I'll just let it run for a bit. Okay, it's done. So we have something like this, which looks quite nice, except some weird parts, but besides those weird parts, it looks quite okay. Let me hide this. So then I can play around with the ISO value to make it thicker or thinner. The smaller the ISO value, the thicker it is. The higher the ISO value, the thinner it is. So I'll just choose 0.75, and then I can smooth it out a little bit, just using mesh smooth with, let's go for 10 iterations. Why not? Smooth it out. It's a bit blobby, a bit too thin. So let's go for 0.5 here. Let's try 15 smoothing iterations. Seems good. Still a bit, a bit blobby here, but it seems okay. So smoothing takes a long time to calculate. If I go to profiler, I can see, oh, actually ISO mesh takes longer, but it's moving as well. 161 milliseconds, so that means for every iteration it's gonna be like 0.16 seconds additional for smoothing. I will just choose data dam to put a data dam here in between my ISO value and my smoothing, just to make sure that it's, you know, clean. And now let's enable preview of the ISO mesh instead. Okay, so we have a definition that works, right? At least on our test object. So now I'll just show everything, select all of the boxes, delete them. I don't need them anymore. Of course, the definition will freak out and will stop working, but that's fine because now we're going to set everything up for this particular element. We need three things. We need our boundary box, right, in which everything is going to be calculated. We need our load boxes, and we need our support boxes. For my boundary, it's going to be quite simple. I will just select the outer perimeter, and I'll just type in boundary, or sorry, bounding box, like that. And where is it? Boundary domain, right click, set one brep, and that's it, right? If I check it, it's here. That's great. I'll just select it, hide it so that it's not in the way. Okay, so now I need to define where the load is going to be and which parts are going to support that load. So first of all, I'll create a support. Yeah, I'll create a support first of all. So I'll just create a box. And let's say from here to here and up, something like this. And now I'll just use scale 1D to actually give it like normal dimensions. So upwards is going to be, let's say one unit, something like this. And sideways, from side to side, it's going to be 0.5, so that it fits perfectly with what we have drawn as a curve. Also, it's symmetrical, so I can just take a copy of it, figure out some sort of shared point that I can use, and there's yeah, I'll just use a quad, I guess, something like this. Okay, so we have two boxes here, and I need two more boxes. So I'll just start creating a box. I'll choose 3-point box rather than a regular one. So a 3-point box from this point to this point to this point, and then inwards by 1. Okay, fine, -1. So it does that, and then I can still do scale 1D from the midpoint to here up until here. Yeah, something like this. That seems good. Let me make a copy. What can we use? What can we use? Oh no, I can just use this, let's see, this point here, and I'll just copy it to here, like that, and then make a, just move it, come on, move this object from here to here. Okay, so I have my box setup done. So now I can go into Grasshopper and reference them in. So again, the bottom one is going to be my support, and this is where the support box is. So right click, set one box, like that. And everything else is going to be how is it called? Load boxes. So I'll just select them, all three of them, set multiple breps, load boxes. Seems to be working. So I'll just check. Okay, that's my ISO value. Let's run it. Boom, 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 boom. It's pretty big though. Like when it comes down to the size of it, it's pretty big, and also, god damn, it's not the prettiest one. Okay, let's see the loads. Okay, so all of the loads are going downwards, and in this case, this whole thing is going to be in different orientations constantly. So what I want is, I want the stresses to be outwards from the center. So this load, for this box, the loads need to go up. For this one, they need to go to the left, and for this one, they need to go to the right. So honestly, I think the fastest way to do it would be, let's think. So these are our load boxes. Instead of using just one brep, I'll just delete it. Come on, delete. I'll create 3 breps. 2, 3. So this one is gonna be a top one, then the second one is going to be to the left, and third one is gonna be to the right. Okay, so I have 3 B reps. And actually, let me disconnect the vectors. And I will entwine them into a data tree. Entwine. Like that. Okay, so now we have 3 data branches with 1 B rep in each branch, and I'll create a vector for each of the B reps, right? And I'll also use entwine for them. Okay, so corresponding vectors. So the first B rep is the box in the top, and I want the vectors for it to be upwards. So that's just simple Z vector, like that. Then the next B rep is the box to the left, and I want the vectors for it. Left hand side is just X vector, like that. And the last one is to the right. So to the right is just a negative, oh, I already have it here, negative version of X vector, like that. So I assume if I just simply connect it like that, it is going to work. Let's check the model. Okay, that's to the left, that's upwards, and that's to the right. Yay! And that supports. Yay! So that works. Also asks us for... the heck is going on there? 1. That doesn't help at all. If I disconnect this, maybe it's going to be cleaner. And reset it, of course. Nope. Okay. For now, I'll just keep it as it is. We'll see if we need to actually get back here and deal with the boundary properties stuff later on. So let's try it out. Let's just see what it does. Okay, connects it like so, connects it into an arc, that's expected, and then just makes a big blob out of it. So this is way too much. Volume fraction, I'll choose to have 0.1 rather than 1. Let's try again. Come on, you can do it. There we go, starts connecting it. And this is all of the iterations that it, like I gave it 30 iterations, so it used up all of them and still couldn't connect it properly. But I think if we just decrease the ISO value a little bit, Jesus, doesn't look that nice. If we decrease the ISO value a little bit, it's going to work. but that looks really bad. Let's see here. Oh, this one is upwards. No. This one needs to be the box in the top. It needs to be pushed downwards. So I'll be using a copy paste. I'll be using a negative version of that. Yeah, that's downwards, and this is to the side. Yeah, so that's that. Back to some adjustments here. Volume fraction 0.1. Actually, I wanna keep it as it is, but optimization iterations, I'll increase this to 40 rather than 30, just to give it some more steps to optimize. Let's zoom in and check. Come on, you can do it. Okay, so it does connect, but that's quite a ugly connection, but I think that's, yeah, that is fine. With the resolution that we have, that is kinda okay, because then we can force it to connect there, and we can later on get rid of that part, which is unnecessary, and so on. Okay, so that works with one box per connection. But in reality, what we have is we have two boxes, right? So one joint here, one joint there, and the same thing goes for every side. So I will take my box and scale 1D, scale it from that point to here, so that I have something like this. Make a copy. From here to here, so I have two boxes there. Same thing, scale 1D, from there to there, copy from point to point, again, scale 1D, where is it? To here, copy, to here, and last one, scale 1D, copy, there we go. So back here, we need to re-reference everything, of course, except the boundary, because we're not messing around with the boundary. So I will just take the two base ones, and I'll just right click, set multiple B-reps. So these are set as my bases. Then I'll select the, wait, which ones are the, so that's the top one, so I'll just choose these two to be my top ones. Ooh, that's gonna be awkward. We'll see. We'll see if we will need to work around it. Okay, so we have two top ones, then we have two side ones to the left, if I remember correctly, then we have two side ones to the right. There we go. So as you can see, these don't work. Well, the directions are off, and that's because even though we're using Entwine, I think we have two B-reps here, so in total we have 6 elements, and here we're using 1 vector per input, so we have 3 vectors, right? 3 directions. So that means that it won't, goddammit, it won't work. We need to have 2 vectors per each input. So we'll need to repeat data, and I'm just thinking of what's the fastest way to do it. Honestly, we can just say measure the length, list length, of all three of the lists that come out of here. So what I'm going to get is 2, 2, 2, and then repeat data. So repeat these vectors this amount of times for each branch. So it keeps repeating it, like it takes vector z, or a negative version of vector z, and then it checks how many times it needs to repeat it. Repeats it 2 times, takes vector x, repeats it 2 times, takes vector negative x, repeats it 2 times. So what we're going to get is minus z, xx, minus xx. Okay, so now, perfect, that works. What the heck do we, why do we have vectors there? I don't know, we don't care. Let's try it out. This is becoming quite big. Okay, reset, run it. Oh, display the mesh. Okay, that seems quite cool. But damn it, there's not enough. Yeah, there's not enough like room or not enough meat for it to work with. I can kinda use, oh, and it doesn't even connect there. I can kinda use lower ISO values to force it to connect, but not good. I'll choose 0.5, and here I'll just instead of using 0.1 volume fraction, I'll use 0.2, like leave me 20% to work with. Let's try again. There we go, this is much better. Something that I would expect it to work. It's somewhat, yeah, because it is somewhat symmetrical, right? That's what we would expect. It does create these kind of weird things here. What are those? Oh, that's a connection like that, which is kind of cool that it does that. Can we keep it somehow? No, doesn't matter. Right now I just want to give you an idea of how to do it, and rather than design it, you know, from scratch. So it kind of looks something like this. And now what I wanted to do, I want to force it, or not to force it, but rather I want to create one more box, which, let me go to top view, it's going to be easier to create it there. I want to create one more box. It's going to be right in the middle of the form, like that. And actually, let me rotate it like so. And this box right here, let me place it somewhere here. I want to, all of the connections that we have here, to definitely run through this box right here, right? I can do that by, instead of using the freaking supports for my boundary properties, I can use this box, right? So brep, set one brep, so now this box is set. Use it like that. Run the simulation. Never mind, I guess. Doesn't work. Okay, that's fine. Because we can just take this box here instead of using this thing. Let me just delete that off. Come on. Delete that off. We can use this box as one more thing that's loading the geometry. So I'll just add it to the entwine here. And for it, I'll just give one more entwine, and I will just say that this box right here is being also loaded downwards. So I can just reuse this negative z vector that I have in my 0, 0 branch. I can just reuse it for this box right here. And now it will definitely work. There we go. Okay. And now I'll start messing around with it. 45 degrees. Run. Okay. Why does it stop running with 16 iterations while I told it to do 40? I think there's some sort of a threshold where if it meets that particular threshold, then it will stop the calculation. So I'll just try to find it. Subdivision threshold for model refinement. All elements which densities are below this value will be deleted. We don't care. Penalty, preventing grayscale result. Difference between next compliances to stop optimization process. Okay, let's try what's the default? 0.005. Okay, let's try 0.001. So it stopped at 16 last time. Let's see if, goddamn, it stops at 13 now. No, keeps going. 20, 21. Yeah, that's good. Now stops at 23. 0.0005. Try again. So this is probably something like how precise does the mesh need to be to follow through the stress lines of the generated stress lines. Seems to be okay. I will be solving some of these issues manually, but most of it seems to be okay. And we get some sort of a blob shape, and you can of course mess around with it as much as you want. Let me smooth it out. Look at the preview. And this is how it looks like once it's smoothed out. Neat. There's one thing that I want to definitely fix, and it's we will be adding, where is it? Come on. We will be adding screws and nuts and so on to this element, just like any other element, right? Let me enable preview and move the screw into the correct position. Move from here to, for instance, here. This doesn't work with the screw at all, meaning that if I go in here, it will collide with the screw and I will need to cut it off and remodel this whole part. So my idea is that Instead of using these as boxes for the load, I will be using a box, like 2 or 3 boxes on the sides, so that there's an opening here. And let's see how that's going to work out. So, time to model again. Delete. What was that? Oh, that's a nut. Okay, delete. Seems fine. 2 points there. Okay. So I'll do it for the. Where do we start with? Let's start with something simple here. I'll make a copy from here to here. Scale 1D to here. So we have one box here. Copy again. Scale 1D, and I'll just give it like 0.5, something like this. And I'll just make a copy from here to here, and actually delete these 2 boxes, right? So this is my top load, and let's just see how it will behave, just to make sure. If it works, then we'll do it for all other ones. Set multiple. Reset, run. Why is it? Oh, I disabled the preview. Come on. It's quite heavy. There we go. Okay, so this is much better because now I'll definitely have enough enough mesh around my joints to actually be able to model out the joints properly. Okay, so that actually works. That's good. Let me just stop the simulation. Okay. Looks horrible though, but that's not the point right now. Okay, so I need to go around the whole thing now and change it. So I'll start with the supports, or actually, can I just make a copy, rotate everything 90 degrees, move the copy down to here, delete. Okay, and then copy to here, scale 1D, from here to here to here, scale 1D, 0.5, make a copy again, from here to here. Okay, so we have that, and then let me copy it to the other side, and now delete the old versions. So now we have something like this going on as our input. So this one was the ones on the left, so I'll just select these, set multiple, that's done. These are the ones on the right, set multiple. This is the one that's just doing its thing in space, so we don't care about that. And also supports, so these 3 are supports. Set multiple. Okay, so we have that. Reset. This time I am going to enable the mesh preview, run it. Okay, everything seems to be connecting. Yes, and the final connection is made. Okay, that's live. So I want this to connect. I could say like 0.23 or 0.22%, not percent, 22% or 23% rather than 20, and then it would probably connect, but I will just choose an ISO value here and I'll just kind of move it down. And now this is a problem. Okay, fine, even less. That seems okay. Yeah, all of that seems a-okay. So now we can smooth it out. Let's see the output. This is a bit too thin as it's being smoothed out. Not a bit, this is way too thin as it's being smoothed out, so I'll use less iterations. Or maybe we should use higher resolution as well. So for now I am going to use the high iteration count. Well, 10 maybe. And I will specify that the limit for maximum displacement of points should be like 1 centimeter, not more than 1 centimeter. Well, that didn't help. Let's do half a centimeter. Okay, that seems 0.3 seems okay. So we have something like this going on. Let me hide this box here just to check. That seems okay as a joint. Hide those. Yeah, I can work with those. Okay, so that all works. The last thing is I will be changing the resolution to something a bit less. Let's say 0.3. I don't want to go lower than 0.3 because it's just going to be too heavy of a mesh. Not of a mesh, but once we make a poly surface out of it, it's going to be too heavy. Let me disable the preview for now and run it. Oh, that's going to take a while. I hope I'll remember to speed up the video for this one, for this part. Okay, it seems like it's done its thing, and this is much better. Like, looks so much better already with higher resolution. That's super nice. Maybe we can even make it thinner. Well, first let's see how it moves. No, there's no need to make it thinner. It's already pretty thin. So now the connections are fine and everything seems to be yeah, everything seems to be okay. I'll maybe even make the limit for smoothing a bit more, 0.5, and iterations I'll increase. What? Oh, invalid mesh, that's cool. Huh. So apparently at a certain point of smoothing, it just breaks. Let's see if we can force it to smooth by combining and cleaning the mesh first, and then trying to smooth it at a higher value. Interesting. What if we do that? No, that won't work. Let's see, why is it freaking out? 3276. That's invalid. Yeah, I don't want to troubleshoot that, so I'll just use less smoothing iterations. Okay, so we have our mesh here. That's done for this particular element. So I'll bake it out into my default layer, I guess. Yeah, I'll bake it out. I'll disable the preview for now. Actually, I'll disable the preview for everything here. And before we close this, because we won't be using this anymore, I'll just group everything so that it's easier to follow through and understand what's going on. Keep in mind that these files are going to be in the video description, so if you want to just download the file without actually creating it together with me, you can through by just downloading it them from video description. So I'll group these and I'll just call them what are these? Load volumes, and then I'll just from top to bottom, top, left, right, and then free floating. Top, left, right, free floating. Okay, so then we have entwine and list length and repeat. Yeah, that's fine. And these are going to be vectors. Actually, let me just add this to the group as well. And these are vectors / directions of load. So that's that. And here just come on. Multiply, not multiply, but make as many vectors as there are volumes, right? So how many volumes we have on each side, we need to have as many vectors here. Then we have volume load, boundary condition, brep. So that guy right there is supports or support volumes. And then we have here domain, which is bounding. Let's say world bounding volume. So define world, and I can call this actually define world, and I'll call this define loads and supports, and I'll call this one define resolution. Okay, so we have all that working. Let me just move these into correct positions. This is not that nice. That seems okay, that seems okay. Then we have model and we have this left. Okay, so model is merge everything into one system. Then we have object, not object, parameters, the Optimus. Optimus, apparently not Optimus. Wait, that's Optimus, that's Optimus. Is that a... maybe that's a grammatical error. Doesn't matter. So this is optimization parameters. And this is analysis parameters used for every optimization step, question mark, because I'm not sure about this. And I'll call this one the brain. And we have meshing of voxel of output voxels, and make it pretty. Okay, so we have that. Now I'll just save it real quick to desktop. I'll save it later for the course. Okay, so we have our mesh here, and we have our inputs here. So let me just clean everything up real fast. New layer, inputs for topos. I'll just take the inputs here. Oh, extrusion. Inputs here. I'll place them into that layer, show selected, these two, this one also goes to that layer, and this one, and then I will call out, actually we don't need anything else, so I'll just delete that. Okay, we have our mesh here. I would want to rebuild this to make it a little less dense, but what the heck, let's just use it as high density mesh. I'll just not mesh it, but mesh to NURB. I'll just use mesh to NURB on it. Hopefully it won't crash my computer. Seems like it's a bit too heavy. Yeah, but it managed to do it, and I'll just delete the mesh. So now this is a NURBS polysurface, and hopefully, if I hide this, do we have any more? No, it seems like it's a single NURBS polysurface. If I type in what, I can see that it's closed, so that's perfect. I can use Boolean operations on it. And it has these tentacles that are waiting for some joinery elements here to connect to. So now I just simply create those joinery elements. Box, I guess, 3-point box from here to here, or actually hide that. Actually, we already have. Nah, we can't use these. I'll need to use the regular ones. The original ones. So 3-point, okay. From here to here to here, inwards 0.5, half a centimeter. Or let's do full-on centimeter. Nah, that's too big. Half a centimeter, 5 millimeters. Okay, so we have something like that. Scale 1D. From here to here, let's see how big does it need to be. I want to make it kind of clean. Now, for aesthetic purposes, I'll make a much bigger box, which is going to be a little bit thinner though. So 3-point from here to here to here, and inwards 0.3, so 3 millimeters. And I'll just scale 1D from midpoint scale 1D from midpoint to here, and let's say 2.5 centimeters to both sides. Yeah, something like that seems okay. And let's see how the connections look like. Well, it fillets a little bit too early, so actually I do need to use 5 millimeters, which kind of sucks, but 0.5, what the heck. Yeah, that seems okay. So I'll use that. Mirror. You don't need to use the mirror tool, you can just copy it, but I'll be using mirror. And then box for the bottom from here to... Okay, now doing this is going to be hell. Let me hide this for a bit. Create a box. 0.5 scale. 2.5. I'm just thinking if there's a quick way. I think if I just grab that point as well and rotate this 90 degrees and move it from point to point here. Yeah, perfect. Perfect fit. So, show selected. This guy. Seems okay. We have something a little organic going on. Now I want to fillet it a little bit and so on before I start messing with Boolean operations. So again, I'll hide this one. Fillet edge. Next radius 0.25. Let's try 0.25. Let's just see. Yeah, 0.25 seems okay. Oops, that's the wrong edge. So I'll go around each of these, like that, like that, that. Oops, that's a no. Like that, and like that. So we have something like this going on, and then, as always, chamfer edge. In this case, I won't use fillet, but rather chamfer, just because it's less heavy, and I want it to be less heavy. So next chamfer distance 0.1. Let's try that. Oops. 0.1, and face edges. I'll be using face edges rather than just regular edge selection, because it's going to be much faster. Okay, we have something like that going on. So now I want to make holes in it as well, or do I want to make it later? Let's try for this one. So I'm going to be using 4mm screws to connect all of this. So here I'll just say diameter of this is 0.4. So I just make a circle. Extrude, curve, upwards, something like that. Seems okay. Make a copy from here to here. Yeah, seems fine. So I'll be using that later. So let me just group these two. Hide. Show selected. Show this bad boy here. And now let's start joining up everything. Do I want to chamfer the inside edges though? Might as well. Hide, chamfer edge, face edges, select, So everything gets chamfered. Now show selected. Oops. Don't need the pipes yet. I'll use Boolean union. I just noticed that, let's see, front view, that this guy slightly extends beyond the voxel here. So I need to fix that. I will just create a box first here, like that. And I'll use Boolean difference to cut away from this guy. Enter with this box. Enter. Oh, this is going to take forever, isn't it? Okay, we have that. Okay. Now I think it's going to work out well. So I select all 5 of my polysurfaces and I use Boolean union on them. Everything seems to be a-okay. Everything seems to be connecting properly. Sorry, everything seems to be connecting properly. Next step, holes for the screws. 90 degrees, move it from that point to here. That's actually, like, this one works really well. Really like it. That's super. Let's see how 4 millimeter, 0.4 centimeters. Let's see how it works on the side. Move from center point, come on, center point to here. Extrude curve inwards, like that. That's perfect. Copy from point to point, like that. Mirror, like that. Oh, that's perfect. Doesn't intersect with the structure at all, except of course where the supports are, but we don't, that's fine. We will solve that in a bit. So that all works. Boolean difference. Okay. So Boolean difference didn't fail, that's great. So we have holes for the screws. One last thing to do is, where do we have that screw nut? And give me the point as well. That is the size of the, how big the nut is. So let me duplicate edge, join up the edge, delete. Okay, so that's the outer portion of the screw. With move vertical, I'll get its center point like that. You can also just type in centroid or volume centroid. I don't remember which one, but you can work with it that way. And honestly, if I just move it here, do something like and is it rotated in a weird way? Oh, come on. Let me just rotate it so that it's flush with some sort of a angle, edge, like that. Okay, move from point to point here. Select the curve, extrude the curve up to some sort of a block like this. So now I don't need the curve anymore. So I have this, oops, this shape here, move vertical, and I'll move it until it reaches the edge of the thing, of, how do I call this, connecting block. And I'll just copy it from this point to this point. So that's a hole for the nut for the other part. I'll just move it up, or no, sorry. I'll select both of these together with the point that's on the bottom of my connection, so that I can easily move it up, rotate it using the move tool, move it from point to point, like that. Okay, so we have, oh, so close, that's nice. Okay, so we have that going on for us, which is great. And now the last bit is going to be taking this, making a copy of it sideways, rotating it 90 degrees, moving from point to point, and then making a copy from here to here. That's perfect. And actually, these don't need to be that long. Scale 1D from here to here. No, maybe slightly longer though. Scale 1D. At least like 2 centimeters, right? Or less. Let's do 1.5. And I'll just make a mirror copy of it. Mirror. Like that. And now it's just simple Boolean difference again. Boolean difference, this, and this. Okay. Let me delete. Some parts are a bit ugly, so if I had the time, I would definitely like cut this away and so on, but actually we shouldn't we? Just for pedagogical purposes, let me make sure that it's at least not broken. Like that. Boolean difference on that one. Oops. Like that. Okay. So now all of that seems to work. Last bit for inserting the screws into a 3D printed part. It's rough with sharp edges, so I'll just use chamfer edge tool with 0.03, let's say. Let's just see how 0.03 will work. Oh god. It's going to take forever, isn't it? Oh no, it's fine. So 0.03 seems to be a-okay. So I'll just go through every hole and make it create this kind of a chamfer for the holes. This just lets me thread in the screw much faster. And if you're dealing with, you know, a physical model that's going to have 500 parts, let's say, right? And each of the connections, come on, enter. Each of the connections are, let's say, 2 screws. So that's 1,000 screws, and you definitely want them to kind of self-align and go in really quickly, just so that you don't waste time. All right, so we have our element, which seems to be done. So now I'll just select it, lock it. I'll select everything around it and delete. Oops, unlock. Selected. So now I'll unlock it, and I have my element type 2. You can see here that due to Boolean operations, some things are, you know, there are some additional lines that are unnecessary. So I'll just select it and use merge all faces. So it's going to get rid of all of the edges that are unnecessary. We wait. We still wait. I should have done a lower resolution model for this, but yeah, it's done now. And this is the point where we start messing around with what's going to be in the top of this element, right? What do we want in the top? Because like inputs for topos, this was our input, which is kind of weird, but actually I'm going to use it. Why not? Yeah. So this is the moment where the tutorial stops, and from here on out it's just going to be me modeling the shape, and maybe by the end of this video I'll also create some sort of a quick render for the intro screen of this tutorial. So let's say, so from here on out you don't really need to follow through. The next tutorial is going to assume that you've already seen 2 more tutorials that I have in my LTH tutorials playlist. And the 2 tutorials that I'm talking about are 2D Game of Life and 2.5D Game of Life. Those were recorded in 2019. So if you haven't seen them, I strongly suggest you do, because you right. So then we have You'll definitely need to have a structure that's that you're going to generate by the end of these 2 tutorials to be able to follow through with the next video that I do. Right, so again, to just repeat, 4.2, like 2019, the second tutorial of 2019, and third tutorial of 2019 are the 2 ones that you want to see. 2D Game of Life and 2.5D Game of Life. All right, so now I'll just quickly model out how I imagine this element could look like. Again, you can imagine it in any other way. And I'll just quickly go, as I'm modeling it and then rendering it, I'll explain what goes through my head, but this is not a tutorial anymore. So I'll just copy the objects to layer just to make make it a bit cleaner. Like that. Let me hide everything else so that nothing is in the way. What could this be? Let's chamfer the edge of this. 0.1, that's gonna be 1 millimeter chamfer. That's too little. 0.5, half a centimeter chamfer. That's good. Maybe even more. 0.75. Like this. Fillet edge. Or no. Extract surface. Duplicate border, offset inwards by 3 millimeters, sure. Join that one back up. Extrude this one. Is it outwards or inwards? Maybe outwards. 2 millimeters. Something like that. And actually, I'll just reuse it. I'll just move it up. Offset inwards 3 more millimeters. Extrude inwards by, if that was 2, then by 4 millimeters inwards. So now this and this gets Boolean union. And then this whole thing gets Boolean difference. Delete that. Ew. This is sticking out. Or is it ew? Huh. Well, actually, yeah, that's fine. We can work with it. So if I have that form here, isolate. If I have that form here, I can kind of draw a cross on it with some additional lines like that. Let's see. I'm just thinking, what kind of pattern do I want to have? No, that won't work. Okay, plan B. Cell curves, CRV, delete, show. Actually isolate, not show. And then just a cross. From it to perp. Offset. Both sides, cap, yes. Flat. Distance, that's 3 millimeters, so it's going to be 6 millimeters. And it offsets like that. Okay, fine. We will use it. We'll use just a copy. 0.3 less 0.2. 0.2, 0.2 here, 0.2 here. So we have that. Trim. Let's get rid of the inner parts. Trim over, join it up. I'm doing this in such a stupid way. What the heck? Join, close curve, extrude curve, just across, show selected, this guy right here. Ah, crap. Okay. Show, isolate. Let's just create a 3-point box, 3 points like that. Copy. Yeah, I'm stupid. Didn't need the cross. Show selected, that one, this, Boolean difference with these, delete, 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 show selected again. Let's see how it looks like. Looks like crap. Why does it look like crap though? That's because these boxes, yeah. Do I want to do it that way though? No, I don't. I'll just do it this way. All the way through. Delete surface with this, join up, Boolean difference. Okay, got stuck there for a bit. Merge all faces, show selected. Let's see how we can connect it. So it already connects, kind of connects there, but I want like 3 connections going on from the center. Show isolate. Isolate from here to here. Copy, copy here. 0.2, 0.2. Loft. Okay, delete. Extrude surface upwards until, let's say it's gonna be 3 millimeters thick. Cap it. Show selected. Show this one. Yeah, that's all I need, right? I think that's all I need. It's gonna look like that, and that seems okay. Maybe it can be slightly moved inwards. Doesn't mess up. That's good. Okay. Boolean union. Okay, so we have that going on, and then let's chamfer edge 0.1. That, and the bottom part of it. That seems okay. Chamfer edge, that, and somehow I'll just go for a wireframe view. That's the edge I want. Back to shaded. Okay. Now we have something like this, and now I can 0.03. So this one gets 0.03, and face edges on this, that, and this face. There we go. Let's check the Arctic view. Why the, oh, right. Disable render of that one. Seems to be okay. A bit ugly here, but that's fine. We will just render it out from some other angle. But that seems to be working quite nicely. Okay. So I'll just use Boolean union. So that works. Render time. And when I'll start rendering, OBS is going to, like recording software, is going to start lagging. So sorry if, you know, if it's gonna become quite messy. But let's see, image height for now, that's fine. Yeah, that's widescreen, that's fine. Environment, I don't want any environment here. Actually, maybe we can use white color for the environment. Let's just see. What the heck? Why is it black? It should read the background color, right, as the light source. We don't care. I'll just create a material for this. For now it's generic, apply to selection, and I'll just create a light source, something like this, from straight up. Okay. Settings, engine GPU, C++ CPU plus GPU, progressive render. Okay. Interesting. Okay, it seems like it was some sort of a issue with that particular file for rendering. I'm not sure what happened, but I just exported this into a separate file and loaded it in, and yeah, seems to work quite well. So now I can continue rendering. So here I'm going to set up a few things. First of all, it's the materials. Generic is fine. Then some lights, slice lights. Let's just do a rectangular light, like so. Move it up. Come on. And turn it upside down. Okay, so it's downwards 100% light, no ground plate needed. And let's go to the settings. So engine, GPU, C++ and the GeForce graphics card. Render output, I'm gonna keep it as it is for now. Environment, don't need a background. Okay, let's just see how it looks like. Seems okay. I don't want a black background for this one. I'll use white. Try again. That seems okay. So now let's find a nice angle to work with. Can we do something like this, perhaps? Maybe slightly. Seems okay. What about other side? Lens length, I'll just use like 35 mil, just to get a stronger sense of perspective for this element. Oop, my bad. Let me zoom out just a tiny bit. Yep. Center it again. Press render. Stop the render. Shush, stop. Render again. Doesn't fit. Like that. Zoom out a tiny bit. Yeah, seems okay. Okay, so we have that going on, going for us. I'll just create a named view, cam1, just so that I don't lose it. Now let's just use a front view as my perspective. And I'll just change the C-plane of it to BXY. So now I have a light source that's going straight down. I want one that's going to be a backlight for my camera. So here I'll just type in camera, and then I'll click on show so that I can see my camera in my new perspective view here. So this guy is going to be a backlight, and it's going to be a unique backlight with slightly warmer tone. Just like that. And it's going to go there. Maybe a bit more narrow. So if the camera is looking at it like that, let's try something like this. Yep. Render. Okay, a few things to change. First of all, my material is very boring. Let's try what can we use? Car paint, metallic. I'll use metallic for this one, maybe. For now, I'll just apply material, and let's make it dark. Maybe it's actually greenish. Less darker, like that. Metalness, let's go for 1, or maybe we can do some sort of a noise. For now, let's have it like this to just see what's going on. Render. Ooh, that's bad. No metal materials for us. Delete that. So instead I'll use subsurface scattering. Apply. Let's see, it looks like that. So what if my scatter color is actually green and my subsurface color is, yeah, that's fine, but overall color is very dark green. Something like this. Apply, render. That's better. It gets that glow, which is nice. The light source is in the way though, so let's make this, first of all, a disk. Second of all, let's make it have a little bit of direction and invisible. That's fine. The scatter is a bit much, and the top light could be a bit less, 75, and could be a bit colder. Scatter scale could be 0.7 instead of 1. Try again. That's good. Yeah, I think that's good. Okay. So we can do the final render. Render output 1080. Camera settings, effects, vignetting. Actually, I want vignetting for this one. So 2. Depth of field, yes, please. Fixed distance, and let's where do we focus? Maybe on let me escape. Fixed distance. Let's focus on this area right there. Defocus 0.225. Let's do 0.35 just to check. Whoa, a little bit overkill with vignetting, so let's do 1. Defocus is too much. Instead of 0.35, let's do. So there it is. That's the final output. Also, while it was rendering, I've set some bloom and glare effects right here. So I just used the intensity of 5.44 and size of 42.65, but you can just vary it any way you want. This is still pretty noisy, but it's good enough as for a splash screen. I don't want to wait that long. So the next lesson or next tutorial that we're going to have is going to be of actually using these elements in a cellular automata system and wrapping them around the cellular automata system. So before we'll begin those tutorials, again, as I mentioned before, I strongly suggest that you look into 2D game of life and 2.5D game of life tutorials that I have on my channel, so that you're prepared and you have enough information to move on with this set of tutorials. So hopefully by the end of the coming week I'll upload a new video, and I'll see you guys then. Bye.